Okay. So last class, what we were talking about is how current is induced due to change in magnetic field. Okay. So we saw that we can induce a current in a current carrying conductor by having some amount of flux change. And to be precise with what I'm saying, I will take you back to the formula, that is this one. Certain change in magnetic field, that is the flux linkage. Flux linkage is what? The total flux across different areas through a coil. Okay, so if there are like 3 coils, then there are 3 times the area. So if I'm talking about just this one area, it's flux. So the net magnetic field through this entire area is the flux. Now what if I'm talking about 3 different turns of coils? I'm talking about the flux linkage. So what I mean to say is the change in flux linkage of flux with respect to time gives us the EMF, or gives us the induced EMF. Okay, so how, if for example in this case that we were talking about in last class, we saw how this change in magnetic flux through these coils, that is this coil cutting through the magnetic fields, is inducing a current in such a manner in the coil that it opposes the effect causing it. So if north is coming in, current will be induced in such a direction that a north pole is created in this end of the coil. Okay, so when the north pole from here leaves, so it looks something like this: north here, south here, and the south is leaving from this end. You know what's created on this end? North pole. Why? Because it wants to attract it. So the flux change over here is such that, well, the amount of flux is, for one thing, decreasing, and that is inducing an EMF. And if I want to consider Lenz law over here as well, a pole over here will be created such that it opposes the motion, right? It opposes the effect inducing the current. So what is the motion over here? South leaving the coil. So what is produced over here? North pole. Why? Because to oppose this motion of going out, I need a north pole to keep the south pole attracted. So I have talked about in brief 2 things: Faraday's law, that due to a change in flux linkage with respect to time, a current is induced in this coil. Second thing is that effect, right, will induce a current in such a direction that it opposes the effect causing it. So when coming in, north pole is created to repel the coming in, and when leaving, north pole is again created over here to attract the magnet leaving the circuit. Now good. Now the one more thing I will add over here: when the north was entering, well, current is in this direction that you see, the red downwards direction that you see, and you know when it's in the middle position, exactly middle, north and south, momentarily the current is 0. Momentarily the current inside is 0, right? And then when it moves out like this, the current is now negative, that is in the different direction. Why? Because a different pole is induced over here. North pole is induced. Initially south pole was induced over here, right? So when it is moving from the middle position to outwards, the current now is actually upwards through the coil like this, which is very interesting, right? So I also show this to you a bit through this graph. Okay, so initially when coming in, current is very little, flux change is very little. Somewhere here, that is somewhere about here, let's say, whatever the position may be, I can't say it with surety because I don't know how this was plotted, but this is a lump sum idea of how current is induced and how it varies around. So when coming in, flux linkage or change in flux linkage very little, so current induced very little. When it is somewhat inside or somewhat near, more flux linkage change, and somewhat over here it is max current, because rate of change of cutting the fields or rate of change of flux linkage is maximum somewhere over here. And I would try to assume that it is when all the magnetic fields are somewhat over here. Sorry, this is the pole. Why did I draw the curve things. So yeah, somewhat over here, when it is cutting through inside at this position, when this motion is happening, when most of the field lines are being cut or entering the coil, this is, I would assume, when you see max current induced, because that is when the change in flux linkage is maximum. So whenever you see maximum change in flux linkage, that is in one position, very little field lines are being cut, and in the next instantaneous point, most of the field lines are being cut. During that position, that rapid change in flux is when you would assume max current to be induced. And when it's somewhat inside again, notice, I will again show this to you, it drops. Why does it drop? Because flux linkage doesn't really change. It is, all the field lines are already inside the coil, right? All the field lines are already inside the coil. The flux linkage is not really changing much, other than obviously being cut through these coils. But anyways, at the exact middle position, it drops down to 0, because flux change over here is pretty much 0. All of the field lines that were being cut is already being cut, and whatever amount of field lines were in the plane normal to the field line is already there. Nothing is changing. There's no change in flux. And also the other thing to note is there's a change in direction of induced current, and that is happening due to the fact that Lenz is said over here. Where is Lenz now? Okay, yeah. Due to what Lenz said over here, that the motion causing, or the flux change causing the induced EMF will be induced in such a way that it opposes the motion causing it itself, right? So think about it. Think of all the words that I just spewed out. Okay, so think of what's happening. What is the motion? Yeah, it's coming in, right? So current will be induced to oppose that coming in. So north is created, and when it's leaving, it wants to oppose it's leaving. So north is created again to attract the south pole. Great. Those are a bit of a review of what we did last class, and the next thing that I want to talk about is how to find the direction of induced current. And over here, what I want to talk about is, look, I mentioned in last class as well, you should be using the right hand Fleming rule. Okay, so the Fleming's right hand rule. You know about Fleming's left hand rule, but over here you use the right hand rule. That is, you use your left hand. This is your thumb, which is same as previous force. This is your B field direction, magnetic field direction, and this, my friend, is your middle finger, so it's your current. Great. So those three fingers are the same. The tags of all those three fingers are the same, no matter the hand. It is simply that we use the right hand because over here, it is not that we are trying to find out the force, direction of force, or we're seeing a change, or we're seeing a force being applied on any current carrying conductor. Over here, what we see is there's an induced current, and there's already a force on the conductor. And what we want to figure out is what direction is the current induced. Previously, current was already there. Over here, a current is induced. And all of these cases where a current is induced, especially generators, so in any case, when the current is induced, we use the right hand grip rule to find the direction of current induced. So please be clear on when to use the left hand rule and when to use the right hand Fleming's rule. Okay, whenever we want to figure out the direction of current induced, or rather, let me make it even simpler for you guys. Whenever a current is induced, to find any of the three fingers, we use right hand grip rule. Sorry, Fleming's right hand rule. Whenever there's a force acting on a already current carrying conductor, we use Fleming's left hand rule. Okay, good. So over here, the example that I was actually showing last class is, look, this is a conductor. This is a piece of wire that is on a plane of field going through. So in 3D, it's somewhat like this. There's a bunch of field going through the plane, so somewhat like this. Okay, and over here there's a piece of conductor, a wire, and this wire I'm moving around through this plane. So once over here, then here, then I'm moving it to this position, then I'm moving it to this position. So I'm basically moving this conductor as it is through different positions on this plane of magnetic field. Okay, so what happens when I move this conductor? This has no current initially, but what happens when I move this conductor around? The thing that happens is it will have an induced current either in that direction, upward or downward. Why? Because there's a magnetic field. There's a magnetic field and I'm applying a force on the conductor, and two of the properties are met, so obviously the third thing will be there, that is a current. And that is one way to say it, and the other way to say it is there's a change in flux, my friend. How, you ask? Look, the conductor goes from this position to this new position, and this is the change in flux. So it, within a span of, let's say, 1 second, it moved an area of, let's say, 10 meter square, and within that 10 meter square there is this change in flux. So initially when the wire was here, right, just positioned here, stationary, that's great, no current in the conductor, and when it moves within 1 second an area of 10 meters square, there's a flux change going on. What? There's a flux change going on. Initially it was 0, now it moves a span, an area span of 10 meters square, and due to this change in area above, or I mean within a magnetic field, there's a flux change. Okay, so it's passing through or cutting through field lines. And how many field lines, you ask? These many, whatever the flux is over in this area. So due to it cutting the field lines or crossing the field lines within this 10 meter square area, a current is induced. Perfect. A current is induced. And in what direction, you ask? Okay, what is the direction? This is the direction of force on the conductor. Magnetic field is inside, so you better use your right hand grip rule now. Okay, so I'll be putting the force, that is thumb will be rightwards, my magnetic field will be into the page, and what you will have is your middle finger pointing in this direction. So that is the direction of current. Okay, so this is one way to figure it out, and I want to show you one other way to figure it out, and that is using the right hand grip rule, where we're directly using Lenz's law. And I'll explain how. So these are the only two methods I will explain. One I explained last class, the other I'll explain right now. And the third method is a bit of a stretch. So you can use it, take a screenshot if you wish, but not needed. Okay? Method 1 and 2 suffice. And method 2 is actually more related to the topic we're going to be talking about. I mean, we're talking about right now. So it's directly related to Lenz's law. Perfect. Good. Give me a moment. Okay, good. So now over here, how do we apply the Lenz law? Let's see. There is a conductor over here initially, and it moves. I mean, the conductor doesn't have a current, by the way. So it moves from here to here. Same thing. It covers a span of 10 meters square. Let's just say. And I want to ask you guys something. In this change of flux that you have, that is change in amount of magnetic fields being cut through, or in this area, what kind of magnetic field did we see increase? And I'll specify what I mean by that. Through this area that the conductor went through, in what direction did the magnetic field increase? I'll reiterate that. When passing the conductor through this area, what kind of magnetic field did it cut through? Was it inward to the page or outward from the page? It was inward through the page. So the flux change that really happened was a bunch of magnetic fields that was going inward through the page was cut by the conductor. So the flux change is actually a certain B field that was inward. Okay? So it was basically a certain amount of B field that was into the page, that was cut through the conductor within this area. So the flux change, whatever the amount is inwards through the page. So the current will be induced in this conductor such that it opposes that change. That is, the current will be induced in this in this conductor such that it produces a magnetic field around itself, such that the magnetic field on this side of the wire of the conductor will be outward or out of the page. Do you see where I'm getting? Since the flux change del phi by del t and EMF induced should be minus del phi by del t. So since the del phi, or the change in magnetic flux, is actually inwards, so the change that happened was inwards through the page, the current induced in this conductor will be such that it creates a magnetic field out of the page. Basically, to oppose the change causing it. So the change is a bunch of flux, a change in flux into the page, that is the change, and the current induced in it will be such that it produces a magnetic field out of the page on this side. Okay, so basically it is going out of the page and then in the page, going out of the page, then into the page, going out of the page, into the page. This is how the magnetic field would look like around the conductor. Okay, so use your right hand grip rule. That is what I'm saying. So you know the change in flux is inward, right? So magnetic field induced will be outward of the page. Will be what? Outward of the page. So you take your right hand and you don't do anything with the thumb. You basically point your fingers, that is the rest of the fingers. Okay, you point rest of the fingers and see what direction the thumb points at. So when you do position your hand above this area and you have your fingers, your four fingers wrapped around like this, so your fingers represent the magnetic field. So your fingers represent the magnetic field coming out of the page, and your thumb will be pointing in this direction. So that shows that the current induced in the conductor will be upwards. Let's take another example actually. Let's say magnetic field was into the page. Okay, and the flux change happened from this position to this position. Okay, so this is the flux change. So what is the flux change? A bunch of magnetic fields were cut through, and those magnetic fields were inwards. Was what? Inwards. So current will be induced in this conductor such that it produces a magnetic field out of the page, into the page. I don't know what I just said. I'll repeat in case I said something wrong. So the magnetic field over here, the dots mean that it is out of the page. Okay, so basically the conductor cut through the magnetic fields that was out of the page. Okay, so a bunch of magnetic field was cut by the conductor that was out of the page. So the change was magnetic field out of the page. So what is the induced current going to be such that the magnetic field in this region is into the page? So the opposite to this direction, that is into the page. So I want to induce a current in this conductor such that in this region, that is left of the conductor, I have magnetic field into the page. So I want there to be magnetic field into the page due to the induced current. So let's see. I'm basically going to use my hand. Okay, I'm going to use my hand and I'm going to curl the four fingers downwards like this. I'm going to point the fingers, so these are actually pointing downwards. These fingers that you see, 4 fingers, are pointing downwards, that is through the page. And this thumb now, what I see, is pointing downwards over here. So the current induced will be what? Oops. Current induced will be downwards in the conductor. So do you see what I'm doing? I basically wrap my hand around, or the 4 fingers around the direction that I think, or I know, the induced current's magnetic field will be. Okay, so I wrap my 4 fingers around the conductor in such a way that shows the induced magnetic field, or the direction that the induced magnetic field should be. Why? Because over here the change of magnetic flux is out of the page, so the induced magnetic field should be into the page. So I wrap my fingers around into the page, and my thumb shows that the current is downwards. Got it? So that's how we can use Lenz law. Okay, that's one way to find it out. That's good, that's great. Hopefully that makes sense. So right till now we have qualitatively understood how to figure things out, how to find the direction of current induced, how to find the magnetic field, and whatnot. Okay, good. Next is a bit different. We're going to quantify everything. We're no longer having a qualitative conversation. We're going to quantify all of that into the real number of, or the real value of EMF induced. So let's try and do that. So basically, okay, over here what's happening? What is the flux change? It is basically whatever the B field is, or the density of flux over here, times the area, that is the flux change. And yeah, that is pretty much the flux change. And then X shows the distance covered by the conductor, and V is basically X by T, so how much distance it covered per unit time. A couple of things over there. So according to Faraday's law, what do we have? The EMF is equals to d phi by dt. Make sense? Okay, I mean negative d phi by dt, but we're going to be working with the magnitude. I want to find out the magnitude is what I'm saying. Okay, so I'm trying to find out the magnitude of EMF induced. Doesn't matter which direction, that is besides the point for now. I want to find the value. So E is equals to d of, that is a small change in BA, then this is basically your phi you know is BA cos theta. Okay, where do we see this? You see this over here. So BA cos theta. N is basically number of turns that you have, and it's more seen with coils. Over here I just have one piece of wire, so it doesn't really matter. So there's no N, and if there's N will be 1. Anyways, this is BA cos theta, which is good, and cos theta, the degree is 90 degrees, so cos theta is 1 over here. Very good. Now what? Now what you have is, I'm going to rearrange this to make this make sense. Why do I say this? Look, magnetic field doesn't change. Does the magnetic field change? Yes or no? No, right? The magnetic field doesn't change. What changes is the area. So I bring the B field out of the bracket or the parenthesis, and I have dA by dt, which makes way more sense because area is changing. Area went from here to here to here to here to here. What changing? Area is changing. Very good. And area I can break down into what? I can break it down into X times L. That is length of the wire, and X is the distance traveled by the wire. So X times L is the area. Very good. Now, is the length of the wire changing? Not at all. It is always this long. So what is changing? The distance, my friend. So X is changing. Very good. So ultimately I can take the L out because that is a constant. So ultimately I have dx by dt. Voila. So what is dx by dt? Distance traveled by the length of wire per unit time. What is that? Obviously velocity. So that is going to be v. Makes sense? Makes sense to me at least. So now what happens if this conductor was at an angle to the magnetic field, or was moving at an angle to the magnetic field? So what I mean by that is, let's say, let me make the visualization a bit easier for you lot. So let's say this is the North Pole, this is the South Pole, and this is the magnetic field, and I have a wire. Okay, so think of this wire being into the page. I don't know how to explain it. So basically there's this wire that is running through the page. There's a length of wire running through the page. So it's basically, I'm looking at it from this side. Okay, so this length of wire looks like a dot to me from here. Are you getting the point? This entire length of wire looks like a dot to me. Okay, so I'm having this look. So I'm having a side view of the entire scene. So this side view, the reason I'm showing this side view is I want to show you what I mean by cutting the magnetic field at an angle. So the magnetic field right now is going like this. Okay, I mean the conductor right now is going like this, perpendicular to the magnetic field. What happens if the magnetic field, if the conductor is going at a theta like this, then you know what happens? So let's say I denote the motion of the wire like this, then it is cutting all of these magnetic fields at an angle. So the flux change in that case, I have to figure it out differently using cos theta component. This is the cos theta component. Okay, and that cos theta component is the ultimate flux change. Hence we say it is going to be BLV sine theta or BLV cos theta. Usually it's going to be the cos theta component or cos phi. So why is it cos phi, or why is it not sine theta, and why can it change between these two? It is basically what you consider theta. Over here, let me show you something. That is, this is, let's say, phi, and this is theta. So if you're taking phi, that is this angle between magnetic field and the normal to the motion. So by the way, this is the direction of motion, and what is the normal to the direction of motion? This is the velocity. What is the normal to the direction of motion? This is the normal to the direction of motion. Normal. Often this can be mentioned as, I don't remember what it is mentioned as. Basically, it is denoting the normal to the plane. Okay, so if the motion is in this direction, the normal to this direction or perpendicular to that direction is in this direction. Okay, and this is basically the direction in which I want the component of the magnetic field. Okay, so hence you have this. So now my point to you lot is, if you're taking this phi, that is between the magnetic field, right, and the normal to the motion, that is, this is the motion and this is the normal, then you're going to use BLV cos phi. Okay, BLV cos phi. Now if the theta given to you is this, oh no, you don't do cos theta, you do sine phi, because you want what? You want the perpendicular component of the magnetic field. So when you're taking this theta or this phi, you just do cos of that phi. Okay, so you get this component. Now when you're taking this theta, then you need to do sine of this theta to get the normal component. If you do cos of this theta, then you get the component of the magnetic field parallel to the velocity, which we don't want at all. We care about the component perpendicular to the motion. Hence, this is again good example, good demonstration. You see, if this is the magnetic field, okay, if this is the magnetic field direction, and let's say this is my bit of conductor, right? Oops, that is my conductor. Let me select this. This is my conductor and this is going through like this. Okay, so the magnetic field is not perpendicular to the motion. So the motion is what? This pink rectangle that you see, parallelogram that you see, is basically the area cut by my conductor. Now what happens is if this entire magnetic field is at a theta, at the phi, to my normal, then we can't just have B times LV to denote the EMF, because the entirety of B is not normal to my conductor's motion. So to have the normal component, we take B cos phi or B sine theta. If you're taking this theta, then it is going to be the sine component to get this, and if you take this phi, then it's going to be cos component of this. Got it? This is simple maths. Okay, this is maths taught in your pure maths. Great. So all of that is good. Okay, so hopefully it makes sense. Most likely this is going to be given to you guys. The phi will be given to you, or the theta closer to the normal, that is the theta adjacent to the normal, will be given to you. This is the normal and this is the theta adjacent to the normal, which is why you use the cos phi component. Okay, hopefully it makes sense. Now what we are starting over here is, well, AC current. Now this is over here, and there is also this same chapter in AC current, which is why I'm gonna look at it for a while and then decide from where I start teaching. Okay, you know what, I'll start teaching from magnetic fields, and then okay, so in this chapter, that is magnetic fields, we have a bit of an extension that is of AC current. And the reason we have this extension is I want to show you guys how AC current really exists, right? So why is it that there is something called an alternating current, where there is current in one direction and the next moment there is a current in a different direction? And you've seen this alternating current shape such as this, you know, a continuous sine or cos graph, somewhat like this, which passes through like that. So you have in the positive axis, negative axis, positive axis, negative axis, so on and so forth. Why does this exist, right? And how do we get this current really? You've seen direct current, that is from a cell, which has a current in only one direction. So for you it makes sense to think that probably that is the only way current really flows, and that is the standard way for current to flow, but not necessarily true, right? So and the way we get alternating current is very related to magnets, magnetic fields, and to be precise, we're going to look at what do you call it, generators. Okay, you must have heard that at some point in your life. You must have heard about generators, how it works, to an extent at least, in IGCSE or just randomly in your home, I don't know. So I'm going to give you a bit of how to, or how this entire AC is generated, right? So it's a bit of a step, and I'm going to go bit by bit. Let's see how you get that alternating current. Again, this is induced current due to change in magnetic flux. So it is induced current due to del phi by del t. So change in magnetic flux with respect to time, you have a current induced. Okay, and now why does it alternate? Let's see. What do you have in this picture? What do you see? You have one, let's say this is one cell or one side of the circuit. So if you have, let's say this, right? Usually in circuit there's a positive terminal, there's a negative terminal. Do you agree with me? Hopefully you do. So these are shaped, or these are devices made in such a way that this that you see is connected to this circle that is able to rotate around and is connected to this part of the coil. Okay, so let's say this is the positive terminal, and then there is another terminal, and then there's this circle, and this is connected to another side of the coil, and this circle is able to rotate. and this, let's say, is the negative terminal. Okay, so this is inflow, so it goes like this. So this is the positive terminal, this is the negative terminal. Let's say if this is the conventional current direction, conventional current, granted that is the conventional current, then yeah, this is positive, this is negative. Good. So basically what I want to say is these are circular sort of coils that you have that is able to rotate. Why do you want these to rotate? Very simple, because I want this entire coil, rectangular coil, to be able to rotate around like this. That is what I ultimately want, and I'll show you why I want that. But I want to just clarify what the setup is. So you have this north pole, you have this south pole, and you have this entire coil, which I have marked in basically a few positions. Where is well, A? This is A. Oops. I've marked the coil in several positions. Just note the positions, please. This is A, this is B, this is C, and this is D. So 4 vertices of the coil I have marked. The reason I do that, I'll show it to you later on. And the coil is rotating in this manner, so like clockwise. Oops. So it's rotating clockwise like this. Fair? So this side turns and moves to that side. Okay, good. Magnetic, by the way, what is A vector? A vector is basically the plane direction normal to this entire coil. Okay, normal to the plane of the coil. Okay, good. So now what is the field line like? Perpendicularly downwards. Valid? Fair. Now over here, I've shown you the field lines, and let's do this. Let's go through a few positions of the coil as it turns. And the reason I do that is I want to show you how the flux changes and how the current is induced. That is moral of the story, and that is where we want to go to. How the current is, what current is induced and why it's induced, and how the coil turns to create that. Look, position 1. What you have? The coil is exactly perpendicular to the magnetic fields coming in, and magnetic fields are exactly normal to the plane, so the flux is max. Okay, flux is max. However, exactly in this position, even though flux is max, the rate of flux change is 0. Why do I say that? Look, over here flux is maximum, but the moment you, let's say, ever so slightly, let's say you just turn this coil, so it has basically turned a bit clockwise, right? Let's say it has turned a bit clockwise. In that case, you know what has happened? There has been very little change in the amount of flux going through the coil. So the change in flux is little. Okay, because still pretty much most of the, or all of the magnetic fields are still going through the plane, as opposed to the change that would have happened if the entire coil was perpendicular like this and it rotated like this. It would start cutting. Right now it is cutting 0 field line, so flux over here is 0. But exactly at this point where it rotates, it will start cutting a lot of a lot of magnetic fields. And that is the reason why over here del phi by del t is max. Maximum change in flux is seen. Okay, so again, let's go one by one, and I have given you the brief idea, but let me just plot the magnetic flux first, and then you will get the bigger picture. So magnetic flux, if not the rate of change of flux not the rate of change of flux, but the flux itself, I'm going to plot over here. So you see Weber over here, that is a net flux through the coil. This is the theta, that is the angle at which the coil is. Initially the angle I'm saying is 0. That's fair. And initially the flux is also maximum. Do you see this? This is max flux. Great. Now it moves to position 2. Over here, what is the flux through the coil? Do you see this coil? Yes, you do. What is the flux through the coil? Magnetic field lines are like this. What is the flux through the coil? 0. Because the plane is parallel to the field lines. So flux is 0. Flux is 0. Now what happens? By the way, notice one thing. This is BA side, and the BA sides are now in top, right? So it is turning clockwise. Now when you see position 3, the entire thing was vertical. This BA side was vertical, right? And now it is basically on the other side. Okay, I don't know why I said A over here. This is wrong. This is C and D, and this is B and A. Oops. So that is the right graph. Good. So what you see right now is the BA on that side, and the normal to the plane is now downwards. So the flux is again maximum, but in the negative direction, because initially the flux, the BA side, it was normal to the plane was upwards, and now when I turn it 180 degrees, the normal to the plane is downwards. You can consider any side of the plane to be the normal, and you can consider that to be the positive flux. Doesn't matter. It really doesn't matter. The change in flux is what ultimately matters, but I have just denoted upwards when BA is in this side and CD is in this side, and this upwards is what I consider to be the positive maximum flux. And then when it completely turns 180 degrees, BA is in that side, and I now consider the flux to be negative. Fair? Okay, good. I mean, the flux has to be negative though, and then you will see that later on. Yeah, I mean, as long as over here it is maximum and it is maximum, that is all that matters. One has to be denoted as the positive, and the other has to be denoted as the negative. That is pretty much the notion over here. Okay, so that is why when you turn 180 degrees, I'm denoting this as maximum flux but negative. Now again, what happens when it's moving 270 degrees, that is position 4, let's say, BA is going to come down and CD moves up. What is the flux over here? Normal is in this direction. What is the flux over here? 0. And again, comes back to the initial same position. That is this one. So BA moves to the side position. That is this. And now again, the flux is what? Maximum and positive. So do you see the variation in flux? You do. You definitely do. Now, can from this you plot the EMF induced? Can you do that? Can you do that? You should be able to. Okay. So over here, what you ultimately have is, what is the EMF? It is the negative rate of change of flux with respect to time, right? Perfect. So ultimately over here, when you have this flux over here, what do you think is the gradient? That is the rate of change of flux with respect to how the theta changes, or even with respect to time. It doesn't really matter. So as time increases, theta also increases. So theta is changing in proportion to time, so it doesn't matter. So over there, what is the rate of change of flux? 0. What is the gradient over here? 0. That is why the EMF induced is what? 0. And then what happens? Then you have a gradient that is negative. Okay, it is not as steep, but still the gradient is negative. So you have a value in the positive axis. Okay, there's a minus sign over here. So there's a negative gradient over here, and that gradient turns into a positive value on the positive axis. Over here, what is it? It is the max gradient, maximum gradient, steepest slope, but negative. But over here, it is going to be the positive value, and it is the maximum EMF induced. And what position is this? 90 degrees. What is 90 degrees? This is 90 degrees. This is the position we're talking about, position 2. And over here, as mentioned to you guys previously, this is where instantaneously, in the next instant, most change in flux happens per unit time, because it goes from 0 to a certain number of flux being through the area of the coil. That is, it is cutting a lot of field lines within that period of time, within that next instantaneous point, right? So it goes from 0 to certain value. As comparison, over here, it already has most of the flux going through it, and even if it instantaneously just moves a bit up, that is, it moves a bit clockwise, the flux change is not really as much, which is why you don't have much of a flux change over here, which is why over here you see the EMF induced being 0. That is, in the coil, the EMF induced is 0 when it's turning from this position. Great. So over here, what do we see? We have in position 2, I have maximum EMF induced, and again in 3, it is 0 because this is the position in 3, which is maximum flux, but 0 change in flux. So again, you have EMF induced in the negative direction now, that is basically over here. So even in this case, the EMF induced will be maximum, but simply in the negative direction. That is alternating current. So you have once the current being in the positive direction, then in the negative direction. So once in the positive direction, then in the negative direction. Make sense? Okay. So it's just the phenomena of the coil turning and the flux changing with respect to time that is inducing the EMF in the coil. Make sense? Okay. So now, for the first half of the cycle, we had EMF induced positive, and then for the next half of the cycle, we have EMF induced negative, and then again back in position 1 where EMF induced is 0. This is how the EMF induced varies with respect to time. This is how the EMF induced varies with respect to time based on how the coil rotates, and that is why you have something called alternating current, because the current over here is alternating based on the change in flux. Now the other thing I still do want to add is, the notion of having negative current. It may not make sense to you as to why, when the normal of the plane is upwards and the magnetic fields are coming through the plane, that is considered positive, and when the entire plate is, let's say the normal is pointing downwards, that is the entire 180-degree flip happened and the magnetic fields are going through. So yeah, in this case the current induced will be negative. So it may not make sense to you inherently as to why this is happening or physically what is happening. Mathematically it may make sense, that is to say, well, we will have a negative flux in one case, which is due to the fact that our normal vector is negative in one case, and in the other case I have the normal vector being positive, because I'm considering up as positive, down as negative. So that in maths makes sense to say, but why is it that the current or the EMF is positive in half the cycle and negative in the next half? Well, to just give you a bit of a pointer over here, let's imagine, or let's think about it in two case scenarios. One is where this is scenario 1, where it is turning from this position, so that is parallel or perpendicular. This coil is perpendicular to all the magnetic fields coming in, and it's going clockwise. And the other scenario is this one, where it is the normal to the plane is downwards, that is, it has already flipped 180 degrees and now it is going to turn further clockwise. So this is scenario 2. Let's analyze these two cases. So what happens in scenario 1? After scenario 1, the current or EMF starts building up in the positive axis. We see current or EMF in the positive axis. What happens in scenario 2, which is basically after point 3, we have EMF in the negative axis. So we have current in the opposite direction. We have what? We have current in opposite direction. This is what we have, and I'm going to somewhat prove this to you and help you guys intuitively think about this. So Notice this, and we're going to use Lenz's law, that is to say we're going to use right hand grip rule to figure this thing out. So when this side BA is turning, it is covering a certain flux. Just think about the line BA. Just what? Think about the line BA. So it is going to turn, right? So let's say it's turning 10 degrees and it is going to move somewhat in this direction, X direction. So the next position will be like, well, let's say it has turned and there's some, well, that's a bad drawing actually. Well, let's say this is the coil position. So the BA side has somewhat moved, that is turned, let's say 10 degrees, 20 degrees, and it is in this new position. So what happened in this case? When BA side BA moved a bit on the rightward side or rightwards direction, what ended up happening? This BA line cut through a bunch of field lines, okay? So the conductor, this side, BA side, cut through a bunch of field lines, okay? And in that case, what ended up happening is the amount of flux change inwards through the plane increased. Similar to the scene with this, right? We call this a flux change. So with just the conductor piece BA, the flux change inward through the plane increased as BA turned 10 degrees in this direction, right, clockwise. So think of it this way. Initially, this is, there is B over here. Like there is B in the front, and right at the back somewhere there is A. And this now turns. And well, this is now B at the front, and right at the back at the other side there is A. So notice that there's a certain horizontal movement. There's a certain horizontal movement which I'm trying to denote over here. And due to that horizontal movement, there's a flux change that is inward flux change. So the amount of field line inward that the BA side crossed or cut increased. So it cut a lot of field lines that is going inward through the page. So the current in BA will be induced such that it produces field lines that is out of the page to counteract this flux change. So the field lines produced should be out of the page. And this is only produced if you form your right hand grip rule, that is, your hand is somewhat like this, right? And your thumb will point in this direction. Your thumb will point in this direction. So it shows, what does it show you? What does this show you? That the current will be in that direction. Fair? The current will be in that direction. So from A to B. Now what happens when I have this position and there's a change happening? So now this is going to turn, right? And this is, let's say, the turn position. That is B. This is A. So there is a certain horizontal movement inward, and it is cutting a bunch of field lines that goes through the page. Fair? Okay. So there's a certain change in magnetic flux. Okay. Fair. That is all good. That is all good. So initially, what did we have? A lot of, current going from A to B. Now, since there's a flux change over here, initially there's a flux change that is through the page, and a current will be induced such that there is magnetic field lines out of the page in that direction. And if I wrap my hand around, you know what I have? Well, I will have current in this direction. Try it out yourself. Basically, I want current to be induced in the conductor BA such that the magnetic field lines on this side is out of the page to compensate for the magnetic flux change into the page. And in that case, if you wrap your hand around properly, like this, you will have your thumb pointing towards A. So that is the flow of current. So it is going from B to A. It is going from B to A during that turn. So all of this shenanigan that I did for you guys is just to prove to you lot that there's a change in current direction as you turn the coil. This is the only thing. This is something that you guys don't realize. You guys will have a tough time visualizing. So this is the intuitive way to think about it as to why the direction of current changes. Once it is positive, once it is negative. Why is this happening? Because the direction of current has changed. Got it? The direction of current has changed. This is why you have a change or a positive axis and a negative axis. So that is in some sense the moral of the story, what is really happening. And this is of course the current graph as well, because V is equals to IR. V is exactly proportional to the EMF induced is exactly proportional to the current induced. So if this is your EMF induced graph, the same graph will also be the current induced graph. Sure, the values over here will be different, but the shape of the curve will be the exact same. Got it? Perfect. The last thing I do want to talk to you guys about is mutual inductance. This graph is wrong. I'll correct this. Okay. Looks about right. And I'll explain this to you guys. No problem. Okay, this one we covered, which is good. And last thing is mutual inductance. What is mutual inductance? Basically, when one coil is going to be inducing a current, an EMF in the nearby coil with a similar setup, let's say. Right? So it's in essence, a coil induces an EMF in the other one. This is pretty much how transformers work. Right? It's the same principle, mutual inductance. So what do you have? We have a AC current supply, that is alternating current supply, and it is such that the direction of current constantly changes. So for the first half cycle, I have current coming downwards through the coil, and the next cycle I will have the current going upwards through the coil, such as that. Okay, and the field lines for half the cycle will be such that there is a north pole over here, south pole over here, and then the next cycle I have north pole over here, south pole over here. Got it? Make sense? Good. Granted that makes sense. Now look at this. Well, initially, as the current is flowing, I know that the current is varying. For even just the half cycle, can you see this? Can you observe this change in current? In this cycle, in this coil only, just this coil, I have a change in current. Okay? So basically what's happening, initially, the rate of change of current is max. So the EMF induced in this coil will be maximum. Why do I say this? Because basically what's going to happen as the current changes through this entire coil, the field lines are going to change as well. So basically this coil will be cutting different amounts of flux, even if you don't change the position of either of them. I'm not moving any of them closer or further away. All I'm doing is changing the current over here. And what that does is it changes the flux inside this coil. So in this coil, there are n number of turns, and the flux itself, what I mean to say is the magnetic field itself changes with respect to time. Why the current changes? Since the current over here changes, the magnetic field lines vary with respect to time. The magnetic field varies with respect to time. Okay, so as that happens, the flux through the coil changes. What happens? The flux through the coil changes. Got it? So it is simply the variation in the magnetic field itself due to a variation in the current itself that there's a flux change through this coil. And since there's a del phi over here, that is change in flux of this coil, EMF is induced through that coil. Okay, an EMF is induced in this coil. That is the secondary coil, coil B. And this, again, Lenz law. What does Lenz law say? That the EMF will be induced such that it opposes the change causing it. So if there is a north pole initially over here, a north pole will be induced over here such that it opposes the change, that is change in the current, change in the magnetic field, right? So in the next cycle, if south is over here, that is in this second cycle, a south pole will be induced in this coil, okay, at least for this side, and over here it will be north pole. Got it? So what's happening is, as the current varies, magnetic field varies, so flux through this secondary coil varies as well, and since there is a change in flux, there is an EMF induced exactly proportional to the rate of change of the flux, and the induced EMF will be opposite or oppose the change of flux causing it. Okay, so that is in summary how you answer a question. They will ask you questions as according to how the transformer works, how the secondary coil EMF is being induced. So if you just notice or play back the last few sentences I said, that is in essence how you answer those questions. Good. So as you see, initially for the half cycle, you have current going down through the coil, and the induced EMF or the current for the same cycle, it will be upwards through the coil. And if you have an voltmeter over here, you will be able to see the EMF induced. That is great. What else? Now let's take a bit of a look at how the graphs look like. So let's say this is the current graph. This is how the alternating current graph. I showed you guys how we get this graph, right? Due to having a constant change in flux, we get AC current. This is the production of AC current. That is why you have AC current supplied to you. Great. So you have AC current supplied to you, and now if this is the current itself in the primary coil, the first coil, so this is the variation of current. Okay, so first half cycle in the positive axis, next half cycle in the negative axis. Very good, perfect, makes sense. Now what happens in the secondary coil? What current is induced in the secondary coil? Okay, so the EMF induced will be minus del phi by del t. Makes sense? Okay, so basically what is ultimately happening is whatever the negative gradient of current I have over here, it is going to be the same value for the secondary coil. And if you just want a bit of proof for that, I'll show it to you over here. I know that due to Faraday's law, EMF induced is negative del phi, that is change in magnetic flux, divided by del t, and the del phi can be expressed as del B times A, that is the magnetic field crossed with the area normal to it. So when you see this cross over here, this is basically the cross product. Okay, so what this tells in essence is what magnetic field I have perpendicular to area, that I multiply with area, and we get a certain value of flux. So cross product basically gives you the product of them, granted we are only considering the perpendicular component of either the area or the magnetic flux. So it is basically perpendicular component of magnetic field times the area. Okay, so that is why often when you see this cross, that cos theta might not be added. It's not necessary. Anyways, ultimately what is B? This formula you don't know and you don't need to know. If they want you to work with it, they'll give it to you. So it is permeability times number of turns of coil times current divided by length. Great. So I include this into the formula, and what do I have ultimately? Let's see. I have this great expression and the normal vector divided by del t. Fine. Great. Now in this entire expression, what do you think is changing? Is normal to the vector changing? No. Is number of turns changing? No. Is the permeability constant changing? No. Is the length of conductor changing? No. Is del t changing? No. We're considering the same change in time, whatever it is. So no. What is changing ultimately? What is changing is the current. Current is constantly changing. Okay, current is constantly changing. Okay, so normal direction of the coil would be like in this direction, so that is not changing. Don't get confused. Okay, so ultimately EMF induced is minus di by dt. So whatever the rate of change of current is, negative of that will be your EMF induced, or your you can also say that same shape will be of the current induced. This is EMF induced. Good. Fair. So now let me show this to you, how we get the graph. Initially, for the primary coil, that is coil A, I have a maximum gradient, and that maximum gradient I take, and I take a negative of that gradient, and I plot it on the secondary coil graph, that is for the current. So this is going to be maximum, but on the negative axis. Now over here, point 2, what do I have? I have a gradient of 0. So the current induced in the secondary coil is 0. Next, again, I have a negative maximum gradient. So negative of negative gradient is what? Positive maximum gradient. Positive maximum value. So I have the positive maximum value, and then the same for this. This is gradient 0, so 0 value over here. This is gradient is maximum, but we take the negative gradient, so it is negative value over here. So this is how the shape of the secondary coil current looks like. Granted, this is the shape of the current in the primary coil. So this is alternating current over here, and this is alternating induced current in the secondary coil. Both of them will have alternating current, and that is always true. Okay, otherwise you can't have induced current, you can't have mutual inductance. In essence, that is pretty much it. And you see this is pretty much what we just explained. You have alternating current through it, so the magnetic field lines vary, so the magnetic field varies, and as the magnetic field varies, the flux through the secondary coil changes, and as the flux through the secondary coil changes, you have an EMF induced, right? And that is why you have a certain EMF or current in the secondary coil. That is great. And why do you have a soft iron core? Like, what's the point of this? This basically, what you see over here, mu naught, it increases that. It increases the permeability. So it's more effective, it is more efficient. So it is high permeability, okay? And it is also true that it is easier to create temporary magnet with having a soft iron core, and it is easy to magnetize, both magnetize and demagnetize. So that is pretty much the use case of having a soft iron core. They may ask you that. So you have 2 points there. And that is pretty much it for mutual inductance. And we just tipped off the topic alternating current. So we just started. We gave you a pretty decent pointer of what alternating current is. So hopefully this would be useful.